Okay, so we up until this point have been using kind of a basic overall definition of acids and bases in our previous solutions unit, okay? In the solutions unit, and previous units when we learned about naming and formula writing, we looked at acids and we named acids. And something you noticed about those acids, perhaps, is that when you write a dissolving equation for an acid, looking at the acids that we have previously dealt with, the dissolving equation included the hydrogen ion on the right side. After the substance dissolved in water, we represented hydrogen ions as one of the things that was made. So, for example, hydrochloric acid. When we wrote the dissolving equation for this guy last unit, we wrote this ion and this ion like so, and then we put aqueous behind them. So we said that this would break into these two ions in a solution where water was dissolving it. And so you can see that, yes, this was an acid and it created the hydrogen ion in a solution, okay? We also looked at some bases last unit. We introduced the concept of bases, our weak bases and our strong bases last unit. A base, up till this point, we told you, was an aqueous solution that contained the hydroxide ion. So something like sodium hydroxide, NaOH, we consider to be a base because it had this OH in it, hydroxide ion. So basic solutions are also sometimes referred to as alkaline solutions. So I want you to be familiar with the phrasing alkaline as well as the term basic. We have acidic solutions, we have basic or alkaline solutions. Sodium hydroxide, for example, like I said, is a base. There are also some other bases that don't have the OH, the hydroxide, in their formula, like ammonia, which is NH3. That is also considered to be a base by certain definitions, like the Bronsted-Lowry definition we will talk about today. So we're going to introduce the concept of those amine bases today as well. And acids and bases are all around us. We have, of course, hydrochloric acid in our stomachs. There are fruits that contain citric acid. If you're, drinking fruit juice, there's citric acid in those fruit juices. Soda also is also slightly acidic because it contains dissolved CO2, which can form carbonic acid. And a lot of cleaning materials, such as the soaps and, different concoctions that you may use to clean your household, also tend to be basic in nature. So we're going to learn a lot more about, the properties of acids and bases when we get further into this unit and when we look at our acid and bases properties lab. But for now, we're just kind of learning how to define an acid and a base. Okay, so that was kind of our overview, what we were looking at acids and bases last unit, how we identified them. With this concept, though, the hydrogen ions and the hydroxide ions, we leave out a lot of substances that we also do consider to be acids or bases. So the first theory that we're going to look at, it kind of goes along with this idea of hydrogen ions and hydroxide ions. We'll also look at the Bronsted-Lowry theory here in a second, which is a little bit more of an inclusive definition in terms of the things that we consider bases. So, this first one, Arrhenius theory. This is the simplest of all of our acid and base theories. Arrhenius theory is really great for quick identification. And Arrhenius theory states the following as the definitions of acids and bases. An Arrhenius acid is a substance that forms the hydronium ion in water. So the hydronium ion is this H3O plus. Okay, this is hydronium. But a lot of times it is used interchangeably with just the hydrogen ion, which is essentially a proton. So as we learned last unit, an acid dissociates and releases hydrogen ions into a solution, just like we saw with our dissolving equation for something like hydrochloric acid. Releases the hydrogen ion into solution. And so in our last unit, we would write the dissolving equation for something like nitric acid like so. We would show the hydrogen ion and the nitrate ion separating out in solution. But what actually happens in a solution where water is the solvent is the hydrogen ions are actually going to go and pair up with the water around it to form this hydronium ion, this H3O+. And so if we were to actually show what happens in an acid-water solution with the dissolving of nitric acid, we would show HNO3 plus H2O, and we would show over here the hydronium ion plus the nitrate ion are what would be created as ions in the water. But again, I said that hydrogen ions and hydronium ions are basically going to show the same thing. So we tend to use those things interchangeably. So if you see, H plus, if you see H3O plus, I want you to be thinking, okay, H plus. That's resulting from the dissolution of something so that there's hydrogen ions in the water, and those hydrogens go and pair up with the water to form this H3O plus. So Arrhenius theory, again, substances that will form this hydronium ion in water. An Arrhenius base is a substance that contains and forms the hydroxide ion in water. So that's our OH minus, is the hydroxide ion. That's one of the polyions you had to learn earlier this year and still need to know. So here in our dissolving equation, we can see that when you drop some NaOH into water, it will break up into sodium ions and hydroxide ions. The benefit, again, of this Arrhenius theory is that it's really easy to sort substances into acids and bases. We basically, like, okay, cool, look, there's an H at the beginning of this, and it's going to break up so that we have this H plus ion and this NO3 ion, which in water is actually going to be looking like this, okay? And then, okay, this guy, very easily we can see there's an OH, there's a hydroxide in there, that's a base. Okay, very easy for quick identification. The problem is that many bases do not actually contain this hydroxide ion, like something like sodium hydroxide does. And so our nitrogen bases, like ammonia, are not actually considered bases by the Arrhenius theory. So we're going to talk about the Bronsted-Lowry theory to talk about a theory that would include those as bases. But before we do that, what questions do y'all have so far? Okay, again, summary. Arrhenius acid, the hydronium ion exists in water. Okay? Arrhenius base, substance that contains and forms the hydroxide ion in water. That's the definition of an Arrhenius acid and base. So, great question. So the question was, is there like a certain theory that's right, or are they all just like different ones? So all of these theories are theories that are used to define acids and bases. Some of them are less inclusive of what we would consider an acid and a base compared to others. So scientists do use like all of these depending on the situation. But what we will use most frequently in this class is we will mostly be using the Bronsted-Lowry theory. This guy's great for quick identification, but we'll do a lot with identifying things like conjugate acids and conjugate bases, which are going to be defined in our Bronsted-Lowry theory. So they're all things that help scientists, sort chemicals and form different substances into categories. And so we talk about all of them because they all have like their own merits and their own advantages and disadvantages, essentially. Good question. Any other questions? Okay. So the second one we're going to talk about, the Bronsted-Lowry theory here. This theory will help address some of the issues that exist with the exclusion of the nitrogen bases. So something like NH3, ammonia, is considered a base with this theory. and it obviously does not fit the Arrhenius theory because we cannot see an OH in this formula here. Okay, so this theory will include this as a base. So let's go ahead and define a Bronsted-Lowry acid. A Bronsted-Lowry acid is going to be a substance that donates a proton. Okay? A substance that donates a proton, and I want y'all to be aware that a proton is a hydrogen ion. Okay? A hydrogen ion is essentially a proton. If you look on the periodic table at hydrogen, hydrogen is right up here. It is, atomic number 1 there. It contains a neutral atom of hydrogen, contains 1 electron and 1 proton. Okay? So when it loses its electron, becomes a hydrogen ion, it is essentially just a proton at that point. So we will oftentimes use the phrase that, a hydrogen ion is a proton, or we will use proton and hydrogen ion interchangeably. So these donate a proton. That is another way of saying that acids lose a hydrogen ion. So they lose an H+. Substances that donate a proton are losing a proton. They're losing a hydrogen ion because they are giving away or donating that proton to something else. So that's another way you can think of it. The substance that remains after a proton is donated is then going to be called a conjugate base. And so we're going to practice more with conjugate bases and conjugate acids in a little bit. But because we can say, once an acid loses a proton, it's now a conjugate base, we have this idea of conjugate acids and conjugate bases that we will address with this theory. And so Bronsted-Lowry theory is used for conjugate identification. So if you are ever asked to identify a conjugate acid or a conjugate base, you need to be thinking, okay, that's Bronsted-Lowry theory that we're working with here. So that means that an acid is something that donates a proton, and its conjugate base is whatever that substance is after it donates that proton. So in this example, for instance, I want you to see, we start with HCl and H2O here, HCl and H2O here, and then over on the other side, I can see that the HCl has lost its H. So now it's just the chloride ion, the Cl minus. Okay? So we're going from here to here. Hydrochloric acid, HCl here. Lost a hydrogen ion, lost a proton by donating it to water. So that hydrogen ion didn't just disappear. You'll notice, compared from this side to this side, the H2O on the left is different. Over here on the right, we have H3O+. So H2O gained a proton, HCl lost the proton. It gave it to the H2O, essentially. Okay? So in this case, this is the acid donated the proton. This is the conjugate base, which is the substance that remained after the proton was donated. Okay? What questions do we have there? Yes, Gabby. Oh, this is short for acid. Yeah, this is acid, and this is conjugate base. Yeah, so that's what the A and the CV. So this is the acid, this is the conjugate base. Any other questions? Cool. Let's go ahead and define a base in Bronsted-Lowry theory then. So a base in Bronsted-Lowry theory is a substance that accepts a proton, okay? So acids donate a proton, bases accept the proton, the hydrogen ion, okay? So accepting a proton, that's the same thing as basically saying bases are a substance that gains an electron, okay? Bases gain bases gain a proton, gain a hydrogen ion. Acids donate a proton or donate a hydrogen. And then, in a similar fashion, having an acid and a conjugate base, we also have bases and conjugate acids. So the substance remaining after a proton is accepted is then going to be called a conjugate acid. So to figure out what the base is, again, we're looking at who accepts a proton. So right here, I see that on this side, I have NH3, I have ammonia. And then over here, I have NH4 plus 1. What's NH4 plus 1, y'all? Ammonium, right? That's that polyion we had to know. So we're going from ammonia to ammonium. This guy has a extra hydrogen, okay? So NH3 gained a hydrogen ion or gained a proton from water. So in this case, since it accepted or gained a hydrogen ion, we would consider it to be a base. So I'm going to put B for base. And then the substance remaining after the proton is accepted is then called the conjugate acid. So I'm going to put Ca for conjugate acid. And so I want you to notice, what do you notice about the charge of the NH4 compared to the charge on the NH3? Yeah, positive. It went up, right? So we went from NH3, neutral, to NH4 plus 1, okay? Well, that makes sense, though, right? Because this guy just gained a proton, so it's going to be one more positive than it was over here. We have one more proton, so we're going to go ahead and, add the extra H, and then now we have a plus 1 charge because we just got another proton. Okay? So, funny story here. The water, since this is the base, the water is acting as an acid here. Okay? Whereas over here, this was our acid, and so the water was acting as a base in this example. So what is acting as an acid, what is acting as a base is going to depend on, what substances are present in the solution. And so here, you always want to make sure you're comparing from your reactants to your product side to see what is acting as the base, what's acting as the acid, because sometimes things like water can act as either an acid or a base depending on the situation. Okay? Water in this situation is acting as an acid because it's going to give away its proton. It's going to become this hydroxide ion. Okay? What questions do we have so far here? Okay, one other thing I just wanted to point out. Notice how we have this two-way arrow. What do we use two-way arrows for, y'all? Weak bases, weak acids. Very good. This guy is a weak base. Remember your weak acids and your strong acids versus your weak bases and your strong bases. If you memorize your strong bases and your strong acids, that's great. You just have to know your strong bases, your strong acids, and everything else is a weak base or a weak acid. Okay? So the last theory we're going to talk about before we start practicing with these conjugate pairs is the Lewis theory. We don't use this theory all that much, but you do need to be familiar with the definitions of a Lewis acid and a Lewis base because you may be tested on that. Okay? So we don't use this all that much. We hardly ever use this theory. But I do still want you to know the definitions because we might ask you a question about the definitions of a Lewis acid or a Lewis base. So one more guy decided to come up with a theory to define acids and bases, and this theory has to do with the electron. The Lewis theory is going to be one of the most inclusive of all the theories. It considers a lot of things, acids and bases, that would not otherwise be considered an acid and base in the Arrhenius and Bronsted-Lowry theories. So his definition was that an acid was a substance that accepts an electron pair around the central atom, and a base is a substance that donates an electron pair. Okay, so this is slightly different from Bronsted-Lowry. In Bronsted-Lowry, we were talking about accepting and donating protons. In Lewis theory, the definitions have to do with accepting or donating an electron pair. Okay, so there is that distinction there. You do need to be familiar with those definitions. This is just an example of Lewis theory being applied. The ammonia here is considered to be a base, whereas the boron trifluoride is considered to be an acid. Because this is able to donate an electron pair, and you can see this bond forming between the two. Just need you to be aware of the definitions there. Accepts an electron pair, it's an acid. Donates an electron pair, it's a base in Lewis theory. Okay? Any questions there? Cool. And let's get a little bit more into practicing with conjugate pairs. We started to talk about conjugate pairs up here. I told you that we identified this guy as a base, and so that would mean that this is the conjugate acid that goes with this conjugate base. And so what we did up here, looking at this example, is we actually identified something called a conjugate pair. Okay? When we use Bronsted-Lowry theory to define an acid or a base, which we are going to do most of the time, when we look at whether or not something is losing or gaining a proton, we can identify it as an acid or base. And when a base accepts a proton, the substance that remains after the proton is accepted is then called a conjugate acid. And we can see a similar thing happen if we talk about the acid definition. We can talk about a conjugate base that goes along with that pair. Okay? So what those are conjugate pairs. And undergoing these processes, losing a proton or gaining a proton, we end up forming what are called conjugate pairs of the original substances. So a conjugate base is what's left of the acid after it donates a proton. It's called a conjugate base because if, we look at that substance, you can see that that would be the substance that would accept the proton in a reverse reaction. So bases are things that accept protons. Conjugate acids are what the base becomes after it accepted a proton, and it's called a conjugate acid for a similar reason. It becomes the substance that would donate the proton in the reverse reaction. Okay, so when we're looking at conjugate pairs, we are going to see two, important things. A conjugate acid-base pair will differ only by one proton. Up here, for example, I showed you that the NH3, the base, and its conjugate acid, they differed by only one proton. I have NH3 here, whereas I have NH4 plus 1 here. This just has one more proton than the base. And the conjugate acid and conjugate base will always be the products. The acid and the base will always be the reactants. So acid and base, arrow or two-way arrow, depending on if it's a weak or a strong acid or a weak or strong base. And then conjugate base and conjugate acid on this side. Okay? So you can see the base, again, if we look at this example down here, I want to show you what is going on. I like to use to identify acids, bases, as well as their conjugate pairs in an example or a problem. What I like to do is I like to look at the pairs on each side. So right here we have HCl, and over here we have Cl-, so a chloride ion without the hydrogen. So these two are a pair, and then I have H2O and I have H3O+, so this is a guy that got a proton. What I like to do is I like to draw some arrows to show what's happening here. Going from HCl to Cl minus, I see that this substance is losing a proton. Whereas going from H2O to H3O plus, we are gaining a proton. Okay? So again, using our Bronsted-Lowry definitions, we can identify something as an acid or base depending on whether or not it's losing or gaining a proton, or a hydrogen ion is another way to name a proton. Okay? So I really like to draw these arrows out and then define that, because if I know that an acid loses a proton, I can very quickly identify my acid and its conjugate base, as well as my base and its conjugate acid. So on the next page, there are a couple of problems to practice this concept with. So I want you to do that for the next three problems. If you get done with those and want to move on to these, you can. But I want you to do these three problems, and then I will do one example here for each of these guys. Again, I'll get this one started off for you. I think it is incredibly beneficial to draw your little arrows out and write who is gaining and who is losing a proton. So go ahead and do that over the course of the next couple minutes, and then we will go over this. Okay, y'all, let's go ahead and talk about these. So from PO4 negative 3 to HPO4 negative 2, what's happening? Are we losing or gaining a proton? Gaining, okay, right? We're gaining a proton. And then that means over here we are losing a proton, right? So what does that make PO4 negative 3 if we're gaining a proton? Give me a 1 for acid, a 2 for base. Hold up your hands. Very good. 2 for base. It is base. This is a base, so that would mean that HPO4 negative 2 is what? The conjugate acid, absolutely. Okay, so that means in this scenario here, water is acting as an acid, and this is its conjugate base. Okay? Again, water's weird. Sometimes it acts as an acid, sometimes it acts as a base. It just depends on the situation. Okay? What about over here, y'all? For HSO4 negative to H2SO4, gain. We're gaining a hydrogen. Very good. So that means we're losing here. So if we follow our, assignment up here, hopefully you got this. Double check your work that you assigned these correctly. Same scenario as above. What questions do y'all have about that one? Okay, and then letter C here. Hopefully you identified these as your pairs. Going from HCN to CN minus, are we gaining or losing an H plus? We're gaining. We are losing. We are losing an H plus from HCN to CN. Now negatively charged. Notice that losing the proton, we now have an excess of negative charge. Okay? So we're gaining the H plus here. So what does that make HCN in this scenario, y'all? An acid, yes. And so CN minus is the conjugate base. Very good. So hopefully you filled in these. What questions do y'all have there? Okay, then I want to go over, let's do We're going to do 3 of these, and then I'm going to do 1 of these with you, and then I'm going to challenge you to do the rest yourself, okay? So first up here, we are given, in example 2, some bases and some acids, and then we are asked to write the conjugate acid and the conjugate base. So if we know, using our Bronsted-Lowry definitions, because that's what conjugate acids and bases and conjugate bases and acids go along with, Bronsted-Lowry, using our Bronsted-Lowry definition of a conjugate base, we can determine what we need to do this guy. With the Bronsted-Lowry definition, does a base gain or lose a proton? A gain. It is a gain of a proton. So bases gain protons, and acids lose protons, okay? So our base here, to figure out the conjugate acid, we're going to have to add another H. And so what we're going to do is we're going to take this, it's going to go from NH3 to NH4. The other thing we have to consider when we start adding or getting rid of protons in a substance is we have to consider the charge. We have now added 1 more positive charge, so NH3 right here, what is the charge on NH3 right now? Neutral, right? It's neutral. So what is the charge going to be if I suddenly add 1 more proton? +1, which you can indicate with just a plus, or you can put the +1 there. Okay? That is the conjugate acid of NH3, which is the what ion, y'all? Ammonium. Very good. So the conjugate acid of ammonia is ammonium. And then over here, we can do a similar thing with our acids, okay? Going to a conjugate base. We just lose a hydrogen. But with what is sometimes confusing with our substances is that they will sometimes have H's in multiple spots. So this guy, for example, we see CH3, NH3 +1. So there's H's here and here. And so students ask, where do I add or subtract the H from? So I have a little, cheat over here to tell you how to do that. For our weird nitrogen bases, like ammonia and things that have, these amine groups in them, for these nitrogen bases, you are going to add or remove the proton from the end of the formula. So anytime you alter an H with one of these guys, you're always going to do it from the end of the formula. For everything else, the H will be added or removed from the beginning of the formula. Okay? So here, losing a nitrogen from the end, we're going to keep this CH3. It's going to become NH2. We have lost a positive, so what is the charge going to be on the conjugate base, y'all? Neutral. It will be neutral because we were +1 here, but we lost a hydrogen. Now we're going to be neutral. We lost a proton. Okay? So we will add or subtract the H from the end if there is a nitrogen base involved. If it is something like nitric acid, HNO3, okay, this is going to be a situation where we add or subtract from the beginning. So since we're losing an H here, we're going to lose that from the beginning, so it's just going to be NO3 now, -1. It's just going to be the nitrate ion, okay? So I'm going to challenge y'all to figure out the conjugate acids and the conjugate bases for these guys here in a second. I want to do one more example with you, example 3, so you know how to fill in this chart, and then y'all can check your work with me after you finish doing everything. So down here for example 3, before you go and fill out the rest of this and then start on this guy, we are asked to fill in the following chart with the appropriate partner, okay? For all of these, 2 of these blanks will stay blank. Will be crossed out, okay? What we want to do is we want to fill in the chart with the appropriate partner. So you need to know that conjugate acids, the other half of the conjugate pair of a conjugate acid is going to be a base, okay? Bases and conjugate acids are part of a pair, and then conjugate bases and acids are part of a pair. So here, the conjugate acid is going to have its conjugate pair the other half is going to be a base. And remember that bases, we can fill this in, bases gain hydrogen, acids lose the hydrogen ion or the proton, okay? So to go from the conjugate acid to the base, you can just take off the H to get this as the base, which makes sense because if this is the base, it would have to gain a proton to become its conjugate acid. Okay? So identifying conjugate pairs, identifying the base, the acid, figuring out the conjugate acid, the conjugate base, you need to know that acids lose the proton and bases gain the proton. The rest, what I want you to do for the rest of these is work to fill these out on your own now. Try and fill in the blanks for the rest of these. I will put up the answers here shortly. If you get done with this before the rest of the class does and you're ready to move on, awesome. There is acid-base naming refreshing practice on the back, okay? So practicing writing acid names as well on the next page, as well as base names and formula writing, okay? So you have 2 pages of naming practice to refresh your knowledge on that after you do these. But go ahead and do these first, and I will come back in a couple minutes with you to check on them. Okay. So there are the answers. Those are the answers. You can check your work. What questions do we have about these? Does anybody need to go through one of these in more detail? Yes, Kaylee. Sorry, repeat your question, please. Uh-huh. Yeah, so basically what the chart, what the chart in number 3 was trying to have you do is identify the other half of the conjugate pair they gave you. So you were, in this first example, for instance, given the conjugate acid. So you had to know the other half of this pair was a base. So the pair goes with the conjugate acid. The base here goes with the conjugate acid. And you know that there's no acid or conjugate base here. The bicarbonate ion is an example of, they're giving this to you as an example of a conjugate base here, okay? And so the acid is going to be the other half of this pair because acids, the other half of a conjugate pair, when an acid is involved, is the conjugate base, okay? That goes back to our definition of a Bronsted-Lowry acid. A substance that donates a proton is an acid, and whatever remains after the proton is donated is then called the conjugate base. So there are only 2 things that make up a pair, since they are referred to as a pair, and so you had to identify, again, that an acid goes with a conjugate base, and a base goes with a conjugate acid, and so you could just mark out these other things since you didn't need to fill that out. Does that make more sense? Yeah? Okay. Any other questions there? Okay. Then on the next page, if you have not already started looking at the acid-base naming, refreshing yourself here, go ahead and do so. This is what I want you to work on the rest of class, along with practice worksheets page 1 and 3. Some of you have, making your way through this quite rapidly. That's awesome. Here, all it's asking you for is the anion formula. So remember, are anions positively or negatively charged, y'all? Negatively. So in this formula, the anion is the bromide anion, so Br -1. The name of that ion is the bromide ion. And so we would use the general guidelines for a "-ide" anion, which is that this would be a hydroic acid, so this would be hydrobromic acid. Okay? So that's what you're going to do for the rest of these. So I'm going to give you the rest of class to work on those along with practice worksheet pages 1 through 3. Okay? When you get done, you can come check your key with me, and you may raise your hand if you have questions.